We finished the last video just as we were about to start talking about FPGAs. So I think that's a good place to start. I'll be using the Xilinx FPGA, and therefore I'll be using a Xilinx development tool called Vivado. Don't worry if you're using a different FPGA or a different tool. The subject matter of this series is pretty generic. First, we'll create a project. I'd like to call it 7th segment. However, the name of the project is usually the name of the top file in the project, and by convention the name of the file is identical to the name of the module in the file. Now, the name of the module cannot start with a digit, so instead I'll do seg7. This is a bit annoying, but otherwise harmless. We'll create a file in system verilog. Concepts covered here are very similar for other languages as well. We'll call it seg7. We select our FPGA and create the project. Next, we need to define inputs and outputs to our module. Don't worry if you don't know what a module is just yet. We'll cover that later. However, it is easier to define those in an editor rather than in this wizard. So I'll just define one input called input 0 and one output called LEDA. Vivado has its own text editor, but I hate it. So I'll be using an external editor for most of my text editing. As promised, I want to duplicate the inputs and the outputs. Here you go, 4 inputs and 7 outputs. Next, I'm going to create a digital version of the truth table. I don't, strictly speaking, need to, but this is a convenience. So what's next? As before, we need to take a column and assign it to the correct output. So we need to write an expression here for all the inputs for which A is 1. I'm going to speed this up, but I will put a stopwatch on screen so that you can see how much time it took in real life. Yeah, that wasn't fun, and that was only one output. 1 down, 6 to go, and haven't enjoyed it one bit. No pun intended. Before we move forward, let's check our work. First, let's assign a value to the rest of them, just so that they have a value. And let's see what we can do with this. Most FPGA tools have something called elaboration, which Vivado calls RTL analysis. And what we get here are all the logic gates we defined in the file. So some inputs are inverted and then fed into AND gates, and the output of those is fed into OR gates until we get a single bit output that should be 1 for all the cases where LED A is supposed to be on. Which is as good a time as any to talk about how FPGAs actually implement logic. Now, in electronics, we call a series of gates that flow in one direction, i.e. have no loops, that only use logic gates, combinational logic. Thing is, this view is very misleading. Our FPGA does not, in fact, have AND, OR, and NOT gates. Instead, the FPGA is something very similar to what we did in the last part of the previous video, where we burned the logic to the ROM in order to encode it. This logic is called a lookup table, or LUT. A typical LUT will have 4 inputs and 1 output, which means that any circuit that has up to 4 inputs can be encoded in a single LUT. If more inputs are needed, we can use a series or a sequence of LUTs, but this part is up to the FPGA to decide. Xilinx actually boasts using bigger LUTs that have 5 inputs to 2 outputs, or can be used as 6 inputs to 1 output, but it doesn't matter because we only have 4 inputs, so we expect this logic to be encoded into a single LUT. So why wasn't it? It wasn't because the elaboration process kind of have nothing to do with an actual FPGA. It just explains what the logic is, what our program said. So our program said this, the elaboration said this. In order to prepare this for loading on an actual FPGA, we need to run a process called synthesis. But before we do that, we have to ask ourselves, these 4 inputs and these 7 outputs, where do they go? Now I've already prepared an FPGA hooked up to a breadboard with 7 outputs connected to the 7-segment display and 4 inputs coming from the power rails. But how does Vivado knows to map in 0 to the correct port? The answer is we need to tell it. That's how. Telling it is done through something called a constraint file. We'll create one now. The constraint file is currently empty, but we can fill it in with something called setProperty. Now it's a bit confusing. The property we're setting is actually on the package pin, and we set it to LEDA. So we're essentially saying the property of the package pin is that it goes to LEDA. But which package pin should we use? If we look at a naked board, we see that the pin to which I connected segment A is A10. So I write here A10. And the rest of them. And we do the same for the inputs. There's one more thing we need to do, however, and that's set the voltage for the pins. Now, it's very important if you try this at home. Most FPGA development boards have both 3.3 and 5 volts outputs. However, most FPGAs cannot accept 5 volts output. So it's very important that you use the 3.3 volt output, as we're feeding the output directly back to the input pins. To set the voltage, we set another property called IO standard, and we set it to LV CMOS 33, which means this is a 3.3 volt port. And we do it for all LED and all in ports. Now we're finally ready for the next step, which is synthesize the design. Synthesis is a step where we compile the Verilog we wrote, or whatever hardware description language we used, and assign it to LUTs and values. So we say, for here we're probably going to say we need a single LUT, and the value pretty much matches the truth table we were using. And when the design is complete, and indeed we see that it used a single LUT. The next step is called implementation, and is usually referred to as place and route. In this step, what we're doing is assigning every LUT used in the synthesis design to a specific place on the FPGA. At this point, we also get a bunch of analysis of our design. Last but not least, we need to generate a bit stream. This is the actual file that the FPGA needs in order to load our design. What you'll notice is that even though this is a pretty lame design that requires no smarts at all in order to synthesize or place, it still took almost a minute to complete. Generation for FPGA is slow. Okay, we're ready to load our design onto the FPGA, but how do we actually do it? How do we move it from the PC to the FPGA itself? So first, we need to power the FPGA. You'll notice that this LED is off. This means the FPGA has nothing programmed on it. Next, we need some mediator, something to transfer the design to the FPGA. The designing tool to do that is called a cable, but is typically referred to as a JTAG. We hook it up to the FPGA on one end and to the PC on the other. And now we can open the hardware manager, connect to the FPGA, and program it. And now we can test whether our design actually works. Of course, we are only getting one LED, but we can check that this LED is behaving the way it's supposed to. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. One thing you'll notice is that if we look at the synthesized design and ask to see the schematics, we will not get the logical tables. We will get a LUT, just like we expected to. LUT 4 means LUT with 4 inputs and 1 output. So now we need to add the extra segments. Except the first one was so horrid, I really don't feel like doing this again 6 more times. So what can we do to make this easier? If you look at the truth table, you'll see something really weird going on here. We took the numbers 0, 1, 2, 3, 4, converted them to binary, and then used them as bits. But come on, this is a programming language or design language or whatever. Surely we can do something simpler. And indeed we can. We can change all of those into a single input that has 4 bits. It's a weird notation, but that's how it works. So now we can redefine this as in equals 0 or in equals 2 or in equals 3 or in is greater or equal to 5. Now this is obviously much faster, but does it produce the same design? If we ask for the elaborated design, this error meant that we forgot to update the constraints. So let's do that now. Now, instead of saying now, this type is called a packed array because the bits in the array form a single number. Reload, and we see a much simpler logic than what we had before, but it's completely different. Now it's based on equality and comparison. Does that mean that the logic will be more complicated after synthesis? Let's find out. While we run the implementation, we will notice that the resources used are still a single LUT. And if we look at the schematics of the post-synthesis, we see that they look exactly the same as before. Single LUT, inputs, output. One difference this does create from before is this. The FPGA is still running the old design. If we look at what happens for the numbers 10 and above, we see that the segment A LED is off for all of them. However, if we now go to the hardware manager and program the device, we see that it is now on for all of them. Which makes perfect sense because that's what we asked. If the input is larger than 5, it should be on. Once again, I remind you that what we do for the values 10 through 15 does not affect whether we're conforming. So with that out of the way, we can do the other 6 segments. Again, let's time this. So it took us slightly less time to do the remaining 6 as it took us to do the original single segment with the old method. Let's generate again. Since on the Xilinx, each LUT can take 5 inputs and map it to 2 output bits, and we need 7 output bits, all from the same 4 inputs, we're using 4 LUTs. That makes perfect sense. Let's look at the schematics. We see that the synthesis schematics actually use 7 different LUTs. Now if we go to the hardware manager, we see that 9 actually gives us a 9, and the rest of the numbers also work. But this logic works. But can we do it better? I think we can. What we've seen with all of the methods we've used up until now is that we've had to transpose the truth table. We've had to actually go over it over the rows, as we were handling one output at a time. But like I said, we have a whole synthesis engine at our disposal. Maybe it can do this grunt work for us. For the next step, we need to tell it that the outputs are directly assignable. And we're going to use something called an always comb block, which stands for always combinational. Always is a very long construct that says we're putting a bunch of code here that needs to be always executed. What we want here is almost identical to the switch case you probably know from software. So we're going case in, and it ends with an end case. And we're putting all of the different options in the middle. So we're giving it a 4-bit decimal number, 0. And if that's what it is, and now we can actually go over the row, because that's the case we're handling. We're handling the case where the input is 0. So we can go LED A is 1, LED B is 1, LED C is 1, LED E is D is 1, LED E is 1, LED F is 1, and LED G is 0. But that's still a lot of work and still error prone. What I would like to do is take the truth table as is and sort of copy it into the code. And guess what? We can do just that. Let's define wire as a 7-bit packed array. And this time, we'll remember to update the constraints. And now we can do a single assignment. LEDs equals a 7-bit binary number, which is, let me just create a template here. So we want the numbers 0, 1, 2, 3, 6. And here we want this table here. Oh. I have no idea why I stopped at 6. Okay, much better. And now we want this table here. I can use regex to remove the spaces, but I prefer to use vim macros. So I'm recording a macro that says take these and delete them, and then move one to the right. And now I can just execute it to pack them all. Let's add a semicolon at the end. We will do that with a regular expression, match end of line, and replace it with a semicolon. And that's it. Let's see what the elaboration says it produces. It doesn't like my use of wire. We'll just replace that with reg. It does the same thing. Essentially has a ROM. We'll see what those are in a second. Let's synthesize the design. If we check the post-synthesis schematics, we can see it looks very similar to what we did before, but actually not identical. We have the LUTs as before, but we also have something called LDCE. And we've also seen under the RTL analysis something called a latch. We'll look at that in a second. In the meantime, let's try and load that and see what happens. So 8 is good. Let's do 1. Let's do 0. 0 doesn't look good. 1 is at the opposite end. It should have been on these segments. 2 is actually producing a 5. What's going on here? What's going on here is that we copied the table as is here, but here A is on the left, whereas the most significant bit of this is actually G. So the segments are in reverse, which suggests we now need to reverse the order of the bits in this table, which is a bummer. But we don't actually have to do that. We can also just reverse the assignment. So if we just go reverse the pins to the bits in reverse order, that should fix our problem. Okay, try again. And we have 2, as we should. Let's check the other numbers. So this is really strange, right? If we do this, 15 produces an 8. However, if we do this, 15 produces a 9. How can the same sequence produce different results? The answer, as you may have guessed, has to do with the latch. A latch is a memory unit, and it preserves the last value it had for certain kind of logic. If we look at the code that produces this, we can see it happening. If we have 0, we're setting the segments that produce a 0. But if we have 15, we don't say anything. So essentially, we're implying that we should still continue to do the same output we did before we got 15. But that's not what we want. We actually got a warning about this we just ignored. Always comb on LED's reg did not result in combinational logic. That was an actual warning we got. Inferring latch for variable LED's reg, line 40. If we go to line 40, that's the first assignment. So what can we do? Since this is a case, we can actually do something like this. But what should we put here? We can obviously put zeros, but that's not an accurate description of what we want. We don't care what happens in that case. If you'll remember, when we did the Carnot maps, when we didn't care what happens, we put in x's. Turns out, Verilog can do that as well. So we can put here. So elaboration now gives us this. In, look up in ROM, out. Post-synthesis schematics also go back to the way it originally looked like. Just LUTs, no latches. If we go to the messages, we see that our latch warnings have disappeared. If we load the design, we see that no matter how we got to 15, it always gives the same result. A random result, but the same one. What you'll notice is that under this design, putting the X's in did not actually save us on any resource. It still uses 4 LUTs, which is pretty much the minimum it can use. However, if our design was more elaborate and used more input bits, in particular more than would fit in a single LUT, then adding access to the undefined cases may reduce the size of your final design. There's one last point I would like to show you. If that was a software design, a more robust solution would be something like this. Set LEDs to all X's to indicate that if that goes out, then you're in an illegal state. And then for all the legal states, put in the values we want them to be. One of the feedbacks I got from people who actually do FPGA design for a living, when they saw something like this, is that I'm writing FPGA code like a software developer. Now, to be sure, that is a fair accusation. I am a software developer. However, this is legal and makes sense. With that said, this doesn't do what a software developer looks at it and thinks it does. So if that was software, what would happen is that LEDs would get all X's, and then we would enter the case, and then LEDs would jump to one of those cases and get the correct value. If that was software and we were to continuously sample LEDs, we would get flickers. But this isn't software. This is an elaborated hardware design. LEDs cannot be assigned twice. We exit the always block after LEDs have been assigned exactly once. Instead, what happens is that the synthesis engine, during synthesis, breaks out all the different options that can happen here and creates, well, this truth table, which to me makes perfect sense. Why should we work hard if the computer can work hard? And indeed, if we synthesize this, it synthesizes correctly, does not produce any new warnings, and produces the desired result. So that's it for this video. In the next video, we'll start talking about introducing clocks into the design. Thank you for watching.